Hi, everyone. Thanks for joining in with us today. Welcome to today's topic, Transformer Protection and Testing Beyond Differential. Here on our webinar platform, you'll find you can move our presentation space around to your liking, as well as discover a few new features, such as learning more about your presenter over here, and being able to contact us offline for any questions you may want to follow up with later, right over here. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be moderating today's presentation and supporting you on any technical issues or questions for our presenter team. On the left side of your screen, you will see the Ask a Question window. You can submit questions at any time during the presentation, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, your certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Sugosh Kuber, Applications Engineer. To assist with the question and answer segment today, we have joining us Abel Gonzalez, Applications Engineer, and Mohit Sharma, Relay Software Applications Engineer. With that, I will hand things over to our presenter. Thank you for joining in today, Sugosh.
Thank you, Michael. I hope you can hear me fine.
Yep.
Good morning, everyone. So today's topic for the webinar is Transformer Protection and Testing Beyond Differential. I'll be turning off my webcam to save some bandwidth for the audio and the slideshow. Okay. So in today's presentation, I would like to talk a little bit more about the transformer protection in general, what different functions are used apart from differential to protect the transformer, like overcurrent protection. We have phase differential, which is the primary source. This is considered the primary source of protection for a transformer. Even within overcurrent, you have phase, ground, negative sequence overcurrents that could be used. There is overexcitation function that is used to protect transformers. And then we also have restricted earth faults that will be discussed in today's presentation. And followed by that, I will talk about the testing aspects of these different functions as to the approach that we take to test these functions, what settings do we consider, what are some test considerations as well, followed by summary. So the question we ask is, what do we protect the transformers from? Obviously, the faults that are in the system. It could be internal faults, internal short circuits. It's a phase fault or a ground fault. You can have external faults. You can have system short circuits, faults on the buses or even on the lines. And then there are some abnormal operating conditions that you would have seen in your system in open circuits. You could have overexcitation condition. You could have an abnormal level of frequency or voltage. And then, you could have a breaker failure or overload. I mean, there are so many conditions that you could face for the transformer protection. And then there are some other situations where they're not fault and they're not abnormal, but they're normal, but they still need to be taken care of when we work with protection on transformer, like inrush and energization, which we will discuss more in detail in this webinar today. Like coordination with protective devices, right? You have multiple overcurrent relays. We need proper coordination for these devices. And then you have the question of security, dependability, and sensitivity. Which protection you want to use? How would you want to coordinate them? Because one protection can come in the way of another. So how would you want to design your protection, right? So that's what we want to address. So here I have a relay that's a transformer protection relay that is shown here, which shows multiple functions inside that relay, which means that relay has different protection functions that can be used to protect the transformer, right? So the numbers you see are the ANSI nomenclature for different protection functions. Like I've listed 3 of them on the right side, but they're not limited to these. There are more which you would use to protect your transformer, like overcurrents 51 and 50, your time overcurrent and instantaneous overcurrent, differential 87, and then overexcitation, the 24, restricted earth fault, the voltage, frequency, and power elements as well. And there are more as well. So this is a single microprocessor relay having all these functions in one relay that you could use. and you might have seen in your substations on your panel where we have multiple electromechanical relays, one each for each of these functions that are used. So depending on what you have in your system, you'll be working with those. So the first thing we'll discuss is the overcurrent protection. As the name suggests, anytime there is a current that goes above a set point of your function, which is an overcurrent condition. So the 51 relays or 51 time overcurrent relays are used to protect in this condition. So we have a transformer where we have multiple relays shown in the system here. The 87 is your differential. Let me get the pointer out. We have the 87, which is a differential. We have a 51 on the high side. When I say high side, it is the primary side of the transformer. So I say high side overcurrent relay. Anytime there is a fault, let's say it's an external fault to your differential relay, the differential only looks at a certain zone of protection. So a fault that occurs external to the differential relay is basically, your through fault. That high side overcurrent protection can provide a through fault protection for that instance. So the 51 also acts as a backup for your differential. Let's say for some reason your differential relays fail to operate, and you always have a backup to rely on your overcurrent relays to operate. Even though it's time delayed, you still have some operation to protect your system. So since I mentioned about the time is very important when we talk about overcurrent. So the overcurrent relays in the system need to be coordinated upstream and downstream. So that is a very important aspect when you deal with the overcurrent protection. And the high side overcurrent protection may not really detect your single line to ground faults on the low side. So next is the low side overcurrent protection. Just like you would have a 51 relay on the secondary of your transformer, which would act as a main for any downstream devices. So if you have a fault on any of your feeders, your main relay would act as a backup in case these relays fail to operate, right? And any fault on the secondary side of a transformer will be taken care of the 51 relay on the secondary. You could have a phase or even a ground 51 relay or a 50 relay to protect from the overcurrent condition. And again, the time coordination is important because we're talking about overcurrent. Time current curves come into picture. You have to properly coordinate them with respect to time and the amount of fault current that is available at each location. So here is a time current curve. We have current on the x-axis and time on the y-axis. So basically, these are some time current curves of different relays that are listed in this TCC. This is just a generic TCC that I wanted to use for explanation. And here you see there is a transformer damage curve. So anytime you want to protect the transformer, your time current curve will be underneath this damage curve. So anytime the current that is the fault current that increases in your system, the relay is going to take care of that before the transformer is damaged. So every time current curve is for a particular amount of current, it would take certain amount of time based on the curve that is selected in your relay. And that's why the coordination part is extremely important. Next is the negative sequence overcurrent. So as the name suggests, this overcurrent function is looking for a negative sequence component in the current, which means, there is an unbalance in the system. There is some kind of fault which would have negative sequence currents in the system. Then this overcurrent function will come into picture. So this can be set for any unbalance in your system between the phases. Negative sequence overcurrent can be sensitive enough to trip very fast on those. Even with the single line to ground faults, you would have some amount of negative sequence overcurrent. It can detect those. The face-to-face faults and open conductor conditions can be detected using the negative sequence overcurrent function. This can be used in addition to what you already have as a phase overcurrent as well as a ground overcurrent to provide more security and sensitivity to your protection, whole protection system, or you could also have like a separate relay itself just to have a new negative sequence overcurrent protection function. And it's been proved that turn-to-turn faults in transformer windings can also be detected using the negative sequence overcurrent function because the negative sequence presence is higher. So next is the ground overcurrent. Like the name suggests, it's a ground or a neutral overcurrent. Different ways it's denoted. It could be 50 G. It's an instantaneous ground. 51 time overcurrent ground or neutral. Different types of ground fault relays are out there that could be used. One of them is a residual earth fault relay. So basically, the earth fault relay is connected to the residual point of the 3 CTs. So we know that a residual current will exist if there is an imbalance, there is a fault in the system that flows to the earth. So that's how you could obtain that fault current, and then the relay can decide based on a set point whether it's a ground fault or no, right? And these kind of relays need to be time coordinated with the downstream relays for sure. And the next type is the sensitive earth fault. It's normally used in systems where your earth fault is limited to a low value. That system would be having some ground resistors, or neutral resistors connected to the neutral point to reduce amount of ground fault that could flow through. So that's when you could use a sensitive earth fault relay. And in this particular relay, basically, it uses like a ring CT, what you call as a core balance CT around the 3-phase conductors, and the relay, which is connected to that, it will detect a very low current, ground fault current, and you could have a setting set really low as up to 1% of FLA. And again, the time coordination for these relays are very important with the downstream. Okay. The next one is the standby earth fault relay. As the name itself suggests, it's a backup ground fault relay. So these kind of relays would have usually longer delay to give it a more time for the primary sensitive or primary residual relays to trip. You could have like a long time inverse curves program this standby earth fault relays. And again, the time coordination is very important in these as well. So the ground over current relay function is used to detect your current flow through the ground connection point on the transformer to detect any ground faults in your system. Next is the differential protection. So in this webinar, I'll be talking about the percentage restraint differential. So a transformer which has its CTs on both sides to monitor the currents on the primary and the secondary, and those CTs are the secondaries of those CTs are connected to your relay to make sure the currents are monitored through the relay, and then if there is a fault, when the differential relay trips for those. So the differential relays, they obviously do some math to calculate what currents are being read, and they come up with the operating current calculation using the current that is read on CT1 and current that is read on CT2, which is the high side CT and low side CT. So and also the relays calculate a restraint current. So the operating current equation is mod of the summation of these two currents, whereas the restraint would be the mod of individual currents that is summed up later, right? So it calculates these currents, and then when the I operate is greater than I restrain by a factor of k, that is when it detects there is difference of currents. Right, because differential protection works on KCL, current flowing in must be equal to current flowing out. So in percentage restraint, it uses a percentage factor of k. So operate must be greater than restrain by a factor of k to be able to detect there is a differential condition to trip. And let's see a couple of examples as to what happens when there are different types of faults, in the transformer nearby the transformers. So when there's an external fault, when I say external, we have the zone of protection is between these two CTs here. Anything between these two CTs would be your internal zone of protection, and then the fault which is external to the zone of protection here. So we'll look into the flow of currents. So the flow of currents is as shown here is the current that's flowing in through the transformer get transformed on a different voltage level that flows out. the currents are balanced. There are no difference in the sense they're balanced and proportional to each other. And obviously the calculations in the relay is such that the restraint current, it would calculate the restraint and operate, but there will be no current flowing to the operate because the currents are balanced and they cancel out. So the I operate will be basically zero, ideally zero, right? Unless you have some system errors or CT errors or so on and so forth. So that's how the relay would not trip for an external fault. The differential relay would not trip. Now, when there is an internal fault, when it's internal again, it's internal to your zone of protection, internal to the location of the CTs. So this is where the fault is, and what happens to the flow of currents is now the current that is flowing in here flows through the transformer. Now the current on the other side now is the direction is reversed and it's feeding into this fault. Now you can see that the currents are summing up such that now your I operate would be a very high value, and then it is a clear internal fault condition. So as long as that the condition is satisfied in the relay, wherein I operate is higher than your restraint calculation with the K factor, the relay would be tripping on the differential because this is a true internal fault. So we were talking about that K factor, the equations for I operate and restraint. So this is the pictorial representation of those equations. This is basically the characteristic itself, where I have the I restraint on the x-axis and I operate on the y-axis. And there is a pickup that is set usually for a differential. So if the I operate is, let's say, as an example number, is a 0.4 per unit. Let's say this is the level of 0.4 I operate. And then we have a slope. Here is your slope, which is nothing but a setting in your relay, which actually is actually drawing a line between your operating region and restraint region, right? So that is what will help the differential relay decide whether it's an internal fault or external fault, right? So this is nothing but your K factor. This particular slope is your K factor, right? So anytime your I operate goes beyond this slope in this region, it's going to operate with respect to your I restraint calculation, right? So it has two regions. And then you could also have a single slope, just like shown here, or also like a dual slope. So electromechanical relays, you would have usually single slope, but in the microprocessor relays, you have the ability to choose multiple slopes here and here. So the slope 2 usually set higher. Let's as an example, let's say 60%. Let's say slope 1 is 30% and slope 2 is 60%. Just for the sake of the discussion, it's set higher than slope 1. Reason is that when you have a condition of CT saturation in the system, the currents are really high, and that is not the case of internal fault for a differential relay to really trip instantaneously. So we give some leeway for the relay to wait and not trip on a CT saturation. So the slope is set really high, and of course, if it goes beyond the slope, it's going to trip after that. So there are some of the challenges that we could encounter when dealing with differential, be it designing the protection or testing the differential. I just want to discuss a few of those challenges here in this webinar. Is the current mismatch that is caused by CTs. We know the voltage levels on the transformers are different, which means the currents are different on each side. So the CT ratios are different. So there is clearly currents are mismatched on each side, right? So how is that taken care of? And then we could have a phase shift due to winding configuration. We could have a delta Y or a Y delta transformer. We know there's a phase shift between one side to another that needs to be taken care of, because the currents that are read by the differential relay considers both magnitude and phase when it looks into the balanced currents on both sides. And then the zero sequence current. When you have a delta Y transformer and you have a ground fault on the Y side, then you have zero sequence components present on one side but not on the other. So that's again a challenge for the relay as to how it would cope with that particular situation. You could have errors due to tap changers, have multiple taps options in the tap changers, and you could have errors due to those. And then the CT saturation is one of the challenges that we already discussed in the slope characteristic as to how slope 2 is used to cope up with the CT saturation condition. And then we have magnetizing inrush, which we'll discuss more in detail about the magnetizing inrush challenge. So the first one is the CT mismatch example. What I have here is a 50 MVA transformer. I have 110 kV on the primary, 33 kV on the secondary voltage. Then when we calculate the primary current, we get 454 amps. And we calculate the secondary FLA, it's the 1,515 amps. So assuming, based on this calculation, assuming these are the CTs that we are going to use that are selected for the primary and the secondary side, 500 to 5 and 1600 to 5. Now let's look what the relay is going to read. So winding 1 current, which is the primary, when we converted it to the secondary, we get 4.5 amps. And then the winding 2 current, the secondary, we get 4.7 amps, right? So clearly there is a mismatch of currents from both the windings, that is on the secondary, that is coming onto the relay terminals. So you have something called a tap selection that you could do, wherein you would choose a tap which is close to what those winding currents are. So in this particular case, you can see that the tap that is close to these are 4.6 for winding 1 and winding 2. So that would be your tap selection in your electromechanical relay. And even with that tap selection, you can see that there's a percentage mismatch of 4.13% because you don't have the option to choose 4.5 in this scale or even 4.7 in this scale, the closest to 4.6, right? So that's the best you can do on electromechanical relay. When it comes to the microprocessor relays, there is some math involved. It uses that to eliminate some errors of these, the mismatch percentage, and then gives the ability for you to choose the exact tap that you want for your transformer protection. So these relays, they will automatically compute all the taps for different windings that uses the transformer information, like the MVA, the voltages, high side and low side, your CT ratios, and all that. So that is how the CT mismatch is overcome in the differential setup. The next challenge is the phase shift due to winding configuration. So we have a transformer DY1 here, which is a delta Y transformer with a DAB connection on the high side. And you see that the CTs are connected Y on the high side and delta on the low side, CT connections. So let us look into how does the currents look. Okay, there you go. How does the currents look on the high side and the low side, right? You see that on the high side, which is the winding 1, these are still it's being on the high side reading. You see there is a phase shift between the high side and the low side. You can see a clear shift, right? Now, when the currents pass through the CT, and then you see there's a secondary current on the relay. Now, both the currents are on the same phase. You see that there was a phase shift on the low side, on the current that is being on the line side and the current that is being read from the CT through the relay, right? So basically in this case, there was no compensation that we had to do for the relay, right? Because the CT connections are solving this issue of the phase shift. The way the CTs are connected for this particular system, it's helping with the compensation itself. So that is one way of doing your phase shift compensation. But what if you have a system where your CTs are connected, Y connected on both high and low, but you have a delta Y involved, which is in this case it's a YD7 with the DAB connection for the delta side, right? So what happens in this case is so the currents that are on the line side, the primary and the secondary, that is how the currents are to start with. Now the relays will also be seeing these currents now. You see there is a clear phase. Obviously there's a differences of phase, right? So the relay would be thinking there is a differential condition, it's going to trip if not taken care of. So obviously we need a compensation to compensate this angle to be able to be in phase with the high side winding, right? So we needed 210-degree counterclockwise compensation in this case to make sure that there is no misoperation on differential because of the phase shift due to the transformer windings here. And these compensations can be provided internally in the relay itself, the relay setting. When design the relay settings, there are different settings to provide your compensation, and different numbers are used for different compensation vector groups. Next is the zero sequence current challenge that we discussed before. Like when there is a ground fault on a Y side, you have zero sequence on one side, but it's not on the other side, right? So the simplest way to eliminate the zero sequence current is to obviously have your Y connected CTs on the side of a delta winding of the transformer, and then vice versa, right? So obviously you have a Y on the delta and delta on the Y. You don't have your zero sequence currents. You don't have to deal with those because they get trapped in the delta windings. So that is one way to eliminate them. But like I said, you may not always have the luxury where your CDs are Y connected. So how would we do in that case? So zero sequence currents in microprocessor relays is removed numerically by applying some compensation matrices. Okay, and again, these are in the form of settings, and then they are from 1 to 12, depending on the transformer connections and vector group. Appropriate compensation matrices need to be used, which would also help with your with your phase shift as well. So let's look how the zero sequence is eliminated using a matrix here. So here is an example. Is where we have a compensation matrix number 1, which represents a delta winding, and then we have the matrix. Then we are using that matrix with your currents that is being read on the relay, right? And then once we get these equations here, we have IA, IB, IC involved. When you represent these phase currents in the form of your positive, negative, and zero sequence currents, these are the equations that we get. Okay, and if you observe that the zero sequence components are canceling out each other in these equations, and then you don't have, it's basically mathematically removing those zero sequence components in the calculations and ignoring that. So it's important to see here that the zero sequence currents are still present in your circuit, but just that the settings are telling the relay how to ignore it. Okay. So next one is the magnetizing inrush. So anytime the transformer is being energized, obviously the transformer would draw really high current from the source to energize the core, right? So, and then this high current is nothing but your inrush current, which is the magnetizing current, right? And obviously you could have it during different situations where you have you're energizing after a complete de-energization. Or you could have a fault, and then once the fault is cleared, you have a voltage that is recovered, and you could see an inrush current during that time. You also could see that during energizing a parallel transformer in the system, right? So this current, like I said, is very high in magnitude. It could be in the order of 10 times or even 12 times your FLA current, right, full load current. And the duration of this is usually a few milliseconds, but it still depends on a lot of factors, like your transformer sizing, your residual flux in the core of a transformer, source impedance, and many other factors, right? This current is transient in nature. Like you see here, here is your inrush current. Inrush current, as an example, if you see it's a very high magnitude current. If you look at your internal fault current, it's obviously your inrush is higher than your fault current in this case. So the differential relay might operate in this case because it's seeing a very high current, right? So the magnetizing this particular inrush current would be only on the primary side when the transformer is being energized, and that is a problem because there is no current on the secondary, and that would lead the differential relay to think that there is some differential condition that is there. So it might trip, which we would say is a misoperation, because this is not a fault. This is a normal condition that we usually see when we energize a transformer, right? So how is that taken care of? So there is obviously the well-known even harmonic blocking method that is used. So the researchers have obviously have done research and found that the inrush currents are rich in even harmonics, specifically the second and fourth harmonics. So the relay, the design protection designers, they came up with this harmonic methods to deal with this, and for example, let's take this as a setting, like 15% of a second harmonic setting. So anytime a harmonic current, the presence of a harmonic current with respect to your fundamental signal, which is a 60 hertz, it goes beyond 15% of the fundamental current, then the differential would be blocked, right? We don't, because then it's an inrush condition. So let's say the harmonic percentage drops off below a set point. Let's say 15% is a set point in a relay. If the harmonic content drops off below the set point, then the differential would come into picture and trip. Maybe there is an internal fault. And what was also done is that the fourth harmonic was also added in the logics to provide more security, because, like I said, second and fourth harmonic both are present during the inrush condition, so both will be used and compared with respect to your 60 hertz signal. And like I said, anytime it's greater than your set point, then the 87 is blocked, so we don't misoperate on differential when transformer is being energized. Right? So in electromechanical relays, they have filter circuits that detect second harmonics to block a differential. Microprocessor relays, like I said, it uses these logics to, again, filters are present, but uses these logics to calculate this particular equation here to see if it's greater than a setting, and then issue a trip if it's less than a setting. So the next is the overexcitation protection. So overexcitation is basically when there is more excitation in the core, right? Which will there will be excess of flux in the core, right? And that will spill over to other areas of the transformer. Now when that happens, there are other components near the core in a transformer that are non-laminated, right? So they're not designed to handle this excess of flux during overexcitation condition, and then which can cause severe heating, right, in the transformer, and then obviously would eventually, your transformer would break down, and you could have a problem with your windings and insulation and all that. So overexcitation is volts per hertz is what is used to detect overexcitation condition. So it's basically volts per hertz is the ratio of your per unit voltage to per unit frequency, right? So some of the causes for overexcitation could be, loss of load to your GSU, right? Or your generators start up at a very low frequency, or you have line lightly loaded and you don't have a proper compensation. So it could be like over voltage, it could be under frequency, it could be anything in your system, but which can cause overexcitation, right? And research has shown that during this particular condition, the signals would have a high amount of fifth harmonics. Okay, so the volts per hertz, indicates the flux, the overexcitation condition. So if it's greater than, let's say, 1.05, your full load, or 1.1 times your no load, then you can say there is overexcitation condition going on, right? And we'll look into this equation here for volts per hertz. So the overfluxing in the transformer depends on some factors, right? So it depends on the cross-sectional area of the core, number of turns, and then your magnetic flux density, right? It depends on all these factors, and that's why volts per hertz is used to detect overexcitation. How would this overexcitation affect our differential, right? Because whenever the core saturation happens, that will lead to your magnetizing current increase in that current, right? And then again, like I said, the currents there would not be current on the low side, the similar current on the low side as we are seeing the magnetizing current on the high side. So obviously we would see that the 87 would come into picture, because we know that the differential relay is going to trip instantaneously. There is no time delay unless you program a time delay. Differential protection is usually instantaneous. So there is no time for even the capacitor banks or voltage regulators to kick in and help with bringing the voltage back to your normal condition. So how is that taken care of, right? We need to look into that. So that's why it's important to have a separate function, like a volts per hertz function, which is a 24, to detect overexcitation, and 87 should not be tripping. So let's see how that is taken care of. Okay, so here we see the slope characteristics of a differential relay. We have a pickup, we have the slope 1 and slope 2. So relay manufacturers have come up with different methods, where one of the methods is to raise this particular pickup level a bit higher when you have a fifth harmonic content in the signal that exceeds a particular amount of setting, right? So by doing this, we still have the differential security of your differential relay intact, right? We are not totally taking it away, but just raising this pickup bar higher. So during this time, the volts per hertz relay, volts per hertz can definitely take care of the 24 condition, the overexcitation condition. Right? The second method is to, obviously look into the fifth harmonic content with respect to your fundamental. And if it gets above a certain set point, then the differential is blocked altogether, right? So these are the two methods that are used to avoid misoperation on differential during overexcitation condition. So for the overexcitation, relay manufacturers would provide some time-based curves, wherein you have for a particular amount of overexcitation, how much time would it take to trip, right? Based on the curves that you would choose. And once you have these curves, the protection engineer would come up with this, where you have your generator limit curve on. This is a time-based curve, and you have your transformer limit curve, which is in the blue color here, and you have a combination of an inverse curve as well as a definite time curve to protect your transformer from overexcitation. So that is how the protection engineers would use those curves and set points to protect the transformer from this condition. Next is the restricted earth fault protection. So like the name itself suggests, it's restricted to a particular zone of protection. So if you see here, we have a delta Y transformer, and we have obviously there's a resistive connection on the grounding here, and we have the restricted earth fault relay that's connected to the CT on this leg, as well as the 3 CTs on the line side. So here is your zone of protection, and any fault internal to this zone, ground fault, right, earth fault we are looking into, would be considered internal. And anything that is beyond this zone is external fault, right? So that's why it's named restricted earth fault. And then obviously it's used to detect your ground faults near the neutrals of a grounded Y-connected transformer. So, and different implementations would be there in different relays that you're using. So it basically uses the currents from the one that I'm going to discuss in today's webinar will be using the currents from the CT on the neutral, as well as the currents from the line CTs as well. So, the element basically compares, you choose one of them as a polarizing signal, one of them as an operating signal. So it's basically like a directional overcurrent function that is used for this particular implementation here. So, which means that it's actually, since it's a ground fault, it is comparing the zero sequence currents, right, on both sides. And then it is based on a set point, it's going to either trip, deciding if it's internal fault, or if it's external fault, it's not going to trip, right? So one other important aspect here is that since we are dealing with the zero sequence currents, the CT connections cannot be delta connected. CTs must be connected in Y. It's a very important thing to keep in mind when dealing with the restricted earth fault. And like I mentioned, it's a directional characteristic that this particular scheme is using. So we have operate current, which is the neutral current, and we have the reference current, or you could call it the polarizing quantity on the line CTs. So the angle between the operating and the polarizing is what will decide whether the fault is internal or external, right? So if the angle falls within this area, which is less than the which is the 90 degrees, it's a little less than 90 degrees. So it's going to detect the internal fault, which you can call as a forward fault, right, for your directional nomenclature. And anytime the angle falls greater than plus 90 or less than minus 90 in this area, it is going to detect it as a reverse fault or a like a external fault. And also, if you can notice here, is that it has some minimum level before which it's not going to operate. right? So which means it has a threshold of zero sequence current it needs to see. As well, there is a supervision of amount of zero sequence with respect to your positive sequence. It's going to see that that has to be above a certain level for this REF relay to trip on a ground fault. Okay. So next we'll look into the negative sequence percentage restraint differential, the 87Q nomenclature. So during heavy load conditions, so the restraint currents that we get from the windings, that makes the phase differential element a bit less sensitive. And studies have shown that to detect the winding interturn faults, negative sequence components are very helpful, are very sensitive as well. So the negative sequence 87Q is used to detect winding interturn faults during heavy load conditions. And we know that the negative sequence currents are not affected by load in a balanced system, right? And this particular logic, the calculation of the operating current is similar to what we saw in the phase differential earlier, where it would choose the restraint currents from the winding 1 and 2, but here it would use the negative sequence currents from winding 1 and 2 during this condition, and use that for the calculation of for the differential calculation. Be it I operate and I restrain, and rest of the logic still stays the same in the sense that you have your slope setting and you have your pickup and all that. So the only difference would be to use the negative sequence current that is present in the system during the fault, right? And this is one other differential that could be used. There is also something called as a combined differential, which would use the phase and the negative sequence both together and provide a single output in a logic. And depending on how you want to design your system, you could choose appropriately. Now let us look into the testing aspects of these different functions. So first and foremost, what I've shown here is just generic connections from a three-phase test equipment to a relay. I show the back of the relay here. Let's see if I can draw. Okay, I've shown back of the relay here where we show the connections being made from the test equipment to the relay. So the connections we need is obviously to power up your relay, you need your voltage source, and then we need to connect the winding 1 current, because you're talking about differential. You would have to make a connection on winding 1 three-phase currents, and then winding 2 currents as well, and the second source of currents on your test equipment. And then you would need a binary input on your test equipment to monitor output contact on the relay, right? So this is the generic test setup to perform differential relay testing. Of course, when it comes to the voltage functions and other functions, you would have to make voltage connections as well. So starting from the overcurrent setting, what are the settings we need to look into, right? So we have a pickup setting of 1 amp. We have a time dial of 5. We also have a curve that we need to test, IEEE extremely inverse. You could have an IEC curve. You could have an ANSI curve, depending on the type of relay you're using. It could be a standalone 51 relay. It could be a microprocessor with all the functions embedded in them. So we'd have to look in those functions, right? So some of the tests we need to perform is, one of them is obviously the pickup test. To perform a pickup test, we know the setting is 1 amp. So we would start to increase a current from 85% of your set point, and then increase in steps here, and with a small magnitude until you see a pickup on the relay for an overcurrent condition, right? For all the three phases here. So once you do that and the relay picks up, it's going to provide you the actual pickup where the relay picked up for the 51 element, depending on the settings you're testing, right? And that's your pickup test. Now we'll look into the timing test. Not just timing or pickup or any test. You can always simulate different types of faults, like a single phase faults or a phase-to-phase or even a three-phase fault when you're doing a pickup or time, right? So you would choose the faults that you would want to simulate, and then choose all the settings that the relay has, right? You are testing an extremely inverse curve with the time dial that is present in the relay and with the right pickup setting. So for the timing test, basically we are testing the time current curve that is programmed in the relay, right? So we have the curve here, and we have 3 points that are chosen on the curve to test, right? Industry standard is 3, but of course I've seen more points being tested on overcurrent on a PCC. So basically, we are injecting twice the amount of pickup, which is a 2 times overcurrent, right? It's a 200% overcurrent, and seeing at this amount of current at 2 times, what is the time it's going to take to trip, right? It's roughly about 46 to 47 seconds where the relay is supposed to trip. So you would perform tests on multiple points like that, repeat the tests for multiple points. And if you observe here, we are trying to simulate a single phase fault on 51 phase element testing. So you may ask that what if I accidentally trip on 51G, which is a ground element, right? Because it's a single phase fault. So so to be able to not trip a 51G but test a single phase fault on a phase element, you would have to perform some phase compensation. Okay, so the way that it is done is that, for example, let's say you want to inject a single phase fault of 2 amps, you would inject 2 amps on the first phase, and then you would inject 1 amp, but at 180 degrees. Again, 1 amp on the other 2 phases, basically. So they're canceling out in the sense it's not there is no zero sequence component really that the relay is going to see. So it's going to see 2 amps, and it's going to trip on 51P. Okay, and then the instantaneous test is similar to your the time over current test, pickup test, but here you would use a pulse ramp instead of a step ramp because you're instantaneous. Since it's instantaneous, the currents are so high, you would just pulse your currents from a very low value all the way to the towards the pickup and keep pulsing and increasing until the relay sees a 50 element pickup. Okay, and if you're dealing with electromechanical relays, then you would have to perform a target and sealing test. So you would need a DC current source as well along with the AC. So the DC current, so once you inject the AC source to your induction unit, so it closes the disk and closes the circuit, then you would start ramping or increasing your DC current source to see at what current your sealing is going to pick up, right? What DC current sealing is going to pick up. You would do a pickup and drop off test for this. Next is the negative sequence over current. Let's say your pickup is 1 amp, you can inject like a negative sequence, right? You see the phase angles, the nominal phase angles would be for your positive sequence would be 0, negative 120, and positive 120, if you see here. But you can inject the negative sequence phase angle, wherein is 0, the sequence is a negative sequence, so 0, 120, and negative 120. So when you inject those currents, you would see that the I2, which is the negative sequence, is at 1 amp, right? So you would start from a very low value and ramp up to 1 amp to see the pickup on the negative sequence 51Q element, right? You could also inject a single phase, just a single phase current to do your negative sequence testing as well. Just that you just have to do it like 3 times what is needed for the negative sequence component to be able to get the pickup for that. Okay, and the same can be used for the timing test. Same values, the same phase angles. Just you would change this one to multiples or different multiples you want to test on your time current curve and perform your timing test. Next is the overexcitation settings. So here is another example, a relay where you have first level of volts per hertz setting as an alarm. Second level is the trip. So you may not see similar type of setup everywhere. You could just have a level 1 and a level 2. It's up to how you would use that for your protection, right? So in this case, the level 1 is alarm, level 2 is trip. So you see the settings is like 1.07 times nominal. That's your pickup. And then 10 seconds is your delay for the overexcitation condition. So you would usually have a higher amount of delay for alarm. And then for the second level, you would trip with very minimal time. Right, so you need the pickup setting, the delay setting, and any curve setting that is used for the trip level. Right, it could be an inverse curve, it could be a definite curve. Right, so we need those settings to test. So different tests we need to perform for a volts per hertz function is that we would do a pickup test, and then we do a time test. This is for level 1, and then the same test we need to repeat for level 2 as well. These are some tests we would perform. So to perform a pickup test, you can again use a ramp function. in here you would inject the voltages such you start injecting the voltages at normal voltage, nominal voltage, which is, in this case 69.28 with a 60 hertz, and then you would increment the voltages up to a higher value so that it would see a volts per hertz ratio, such that's an over voltage condition. It would see a volts per hertz condition, like over excitation, and then pick up on that condition, right? So you could either do over voltage or under frequency for performing the test, right? And once you perform the pickup test, let's say the pickup was 1.07, and then depending on what you inject for the voltages and the frequency, appropriate measured volts per hertz, wherever the relay is stripped or picked up, it's going to be shown in your report. To perform a timing test, you again, like I said, so it could be an inverse, it could be a curve, it could be a definite time. You can choose multiple test points on your curve, and then you could choose. So it could be like twice your 2 times multiple of your actual volts per hertz pickup, right? So then you would have to change your voltage and frequency such that it's twice volts per hertz of your pickup. And once you inject that, like it's shown here, this is a definite time function. Once you inject that 2 times this 2.14 volts per hertz compared to your pickup, you'll be getting a, it's expected to trip within 1 second, no matter which multiple you choose. It's a definite time. So all you do is basically set up a pre-fault with nominal conditions, and you have a fault state wherein it will inject the 2 times or 3 times or whatever multiple you choose to inject the currents for, so inject the signals for the overexcitation test. And again, you could do this with over voltage, under frequency, how you choose to mimic that pickup level of different overexcitation conditions. So next is we have the transformer differential. So what settings do we need to look into the transformer differential testing is obviously the transformer rating itself, how the CTs are connected on both the windings, and what are the CT ratios, right? And then voltage levels, obviously, on both sides of the transformer, right? Following that, we would need to look into the taps itself, which are usually auto-calculated on microprocessor. And you saw the taps on the electromechanical relays, which you can see on the front of the relay itself, right? And then you would need the pickup setting. Remember, we had a pickup setting for the operating IOP. And then you have the slopes. We could have multiple slopes. You could have one slope. You need to have the slope settings to test. And then there is a breakpoint between a slope 1 and slope 2. You could have unrestrained element current set to, usually the unrestrained function is used to, trip on a very high internal fault of very high magnitude, right? So these are usually set very high. In this case, you see it's a 10 per unit, 10 times per unit, 10 times. So that is one thing, as well as then second harmonic blocking. Remember, we discussed about the second harmonic, fourth harmonic, and fifth harmonic. So these are some settings we need to look into before testing the differential. So obviously those settings and transformer information needs to be translated onto your testing platform, right? So we need to make sure all the information we enter of the transformer, importantly, the connection type. Some of these things are really important. We have to cross-verify things to the connection of the transformer itself, and then obviously the CT compensation that is used in the relay. So we need to use the right vector group here to be able to inject the right amount of right set of phase angles on each winding. And then when you do a single phase test on differential, and especially when you have delta Y or Y delta transformer, it's important to use the right single phase pickup factor on each side. So you have a proper compensation of magnitude, right? So this information, you can get it from the relay manufacturer's user guide or manual. You can double check that depending on what relay you're using in testing, right? And then obviously we have to translate all the differential settings, the second harmonic and pickup, and the fifth harmonic, as well as importantly, right kind of slope that the relay uses that we need to choose, and the restraint equation that the relay is using to calculate from the currents that it's getting from both the CTs, right, both the windings. It's very important to choose the right restraint equation, and obviously the slope settings are also translated here in the test platform. Once we do that, here are some of the tests that you can run. for differential validation, right? The first thing is a stabilization, which will help to determine if our test setup is correct, not just on the test platform, but also the actual physical connections from the test set to the relay. And then, so if you look here, so we are injecting a nominal condition. These were the tabs, right, on this particular relay. So we're injecting nominal condition, and then we see that the currents have to be balanced, and then the relay should not trip on differential when you're trying to inject these set of currents, right? So that is what the stabilization test does to make sure that our test setup is right. If there is anything wrong, obviously we would see that the I operate would be higher and the differential current would trip because we are not injecting balanced amount of currents. Right? Next test is the pickup test, where we would, we had the setting of 0.3. Remember, there was the pickup on the characteristic that we discussed. So basically, we can do it as a single phase test, also as a three-phase test. So for a 0.3, we are injecting this much amount of current. How did we arrive at that current? Because 0.3 is a per unit setting, so we need to convert that into amps. So our tap was 4.17, so which translates to approximately 1.25 amps of pickup. So that's what is done here. Is current lower than 1.25 is ramped on A phase on winding 1, and it's ramped all the way until the relay picks up on the 87 element, because the setting is 0.3 per unit. And the same test is repeated other phases and three phase. You can notice that in the winding 2 pickup test, then obviously the pickup value is different for the single phase and then for the three phase. So obviously for the three phase, we don't need to, there's no compensation. But for the single phase, if you look here, we are using the single phase pickup factor along with the per unit and the tap calculation. We're using the factor as well, and then using that current to use for the single phase pickup factor. In this case, it's √3 on the winding 2. Then we would perform a characteristics test. So we perform. Okay, so we perform the pickup test here. Right? The first one was a pickup test, and then now we would need to perform the slope test. Right? So we need to perform the slope test. There are 2 slopes here, so we can choose different points on the slope, like you're seeing here. So each point would, for a particular amount of restrained current, what is it? So this is the operate current that is required for the relay to see a differential condition, right? So for every point, what we're doing is we're injecting a set of currents on winding 1 and 2, such that obviously the operate current is higher than restrained by this factor of slope, which is 25% in this case, right? So the moment we ramp the current such that the operate quantity goes higher than the slope, the relay trips on differential. And the same test is repeated for multiple points here on the plot. Let me change this. Okay. Then we have the characteristic short test. We validated the pickup, the slope lines themselves, the boundary. You can operate in restrained region, but you can also choose a set of currents to validate these points here, right? It's like a go or a no-go test, where you straight away inject current such that the operate quantity is right here, and then the relay is supposed to trip for these operate points, and the relay should restrain for these points on here, because the operate is below these slopes. This is in the restrained region here, right? So this is another test you can perform. And then we have the second harmonic block test to make sure the transformer differential does not trip during energization, right? So what we do is we inject a fundamental current along with a second harmonic current, right? So we ramp the second harmonic current such that the moment the second harmonic content compared to 60 hertz goes below the 15 amps, it's going to trip that there is a differential condition, because 15% let's say is our setting, right, for a second harmonic. So anything that's beyond 15%, we know that the transformer energization is a normal procedure, so we don't trip differential on that. And that is what this test is. We have done that single phase. You can do it in 3 phase for both winding 1 and winding 2. Okay. And then we have the nth harmonic short test, which is the 5th harmonic test. And this is a go or no-go test that you can perform. You could also do a ramp test, but you could also do a go, no-go test here, wherein we will inject a harmonic content of about 40%, and also 30% in other tests. So we're checking that the relay should not operate for 40%, it should operate for 30% because the setting is 35. And that's what we're doing here in these columns, is we're injecting the fifth harmonic currents along with the fundamental. The moment it's 30%, obviously it will operate, and for 40 it will restrain from operating. And we repeat those tests for all the phases as for both winding 1 and 2. And then we have the restricted earth fault setting testing. So we look into the settings here. Is you can choose which winding you need the operating quantity from, right? If your Y is on the primary, Y is on the secondary, you would have to appropriately program your protection. And then, like I said, there is a supervised tripping. The ratio of your zero sequence to your positive sequence must be above this set point for the restricted earth fault to operate, right? That's the minimum it has to see. And also here is your threshold for your residual current, the sensitivity threshold, the minimum pickup, right? So here, these are the tests that you have to perform, which is the angle test, right? And then the pickup test and timing test, right? So like I said, the REF here uses a directional comparison. Like, we need to look into the angle between the operating current and the polarizing current. So that's what we have set up here. Is we have on one side we have the currents from the line side, on one side we have the current on the neutral CT, and then we would change the phase angles. We change the phase angle, so it's right now at 90 degrees. We change the phase angles such that it reduces, and it comes in the area of your internal fault, right? Then we expect the relay to trip at a certain phase angle, and that's what we test in this angle test. And you would also have to do it counterclockwise and clockwise both. You can also repeat that test in the other direction as well, and in this area as well, when you perform the angle test. And then for the pickup test, we know the setting is 1 amp, so you would inject a value and then ramp such that it's closer to that 1 amp where the relay sees a pickup on your earth fault, right? So that's what we do in the pickup test, a straightforward ramping of current. And for the time test, this particular implementation is based on the inverse curve. So you would have to do the multiple point tests on these curves. You could do a multiple of the pickup and see how much time would it take to trip on the earth fault for the restricted earth fault scheme itself, right? So these are the 3 tests you will perform here. Here are some Megger test products that I would like to show today. Here is the SMRT1, which is a single phase test equipment. And here multiple SMRT1s are shown. These SMRT1s can be daisy chained together to form a 3-phase test set. We also have 3-phase test equipments, different models with more than 6 currents and more voltages and all that, depending on what is the need for testing. We also have these equipments with the display, without the display. So if you choose not to use PC, you can use the one with the display for your testing needs. So I'd like to conclude my presentation with this summary slide. So what we'll learn so far today is the transformer electrical protection that needs to be addressed from obviously the fault conditions. We have to take care of those, and then different abnormal operating conditions that we discussed today. That's why we need protection on a transformer. We looked into the overcurrent protection, the phase protection, time coordination importance between the different 51 relays, and we see that the overcurrent can act as a backup in case your differential relay does not trip in the first instance, right? And then negative sequence overcurrent, we looked into that, which can provide more sensitivity in the protection for unbalanced conditions. And then the ground fault protection is used with systems involving wire winding, where you have the ground source for a ground fault, or path for a ground fault, right? We looked into different types of ground fault relays, and then differential protection, I discussed the operating principle, percentage restraint characteristic, how differential relay would operate for external and internal fault, and did discuss the different challenges one would face when dealing with differential, like phase shift, CT mismatch, magnetizing inrush, so on and so forth. And then also discussed about the restrictor fault can be used to protect transformers from ground faults as well. And then I discussed about the testing aspects of these different elements, which involved obviously the metering check, which would help with the connection check, and then be it any function that we discussed today, you would perform a pickup test, a timing test, and then you would perform different tests to validate the different characteristics itself. Characteristics would have different areas, different settings that would define a characteristic. So you would perform different tests, like we discussed today, the characteristic test, the second harmonic test, and to validate your complete protection scheme. So that concludes the presentation.
All right, excellent. Thanks, Agosh. So as we conclude our presentation, we'll be getting into our Q&A segment here in a moment, where we're going to field as many of your questions as we can live. For those of you that are leaving, please be sure to fill out that survey before you do. We would greatly appreciate hearing how we did today and how we can improve upon our future webinars. Additionally, on that survey, there's a field for you to request a quote or a demo on any Megger products. A copy of this presentation, certificate of attendance, and link to the recording of our webinar will be sent in about 2 business days to everyone here in attendance. Before we switch off, I'd like to remind you that you can also view video recordings of our previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our webinar next month on May 20th, titled The Primary Injection Testing of Switching Devices with Vacuum Interrupters, presented by Daniel Carreño. All right, well, let's jump into our questions. The first one I have, I'm going to be throwing over to our presenter, or our panelist, Abel Gonzalez. And I'll invite our panelists to jump back on the camera so we can see your beautiful faces. Abel, how do we detect and protect the transformer against saturation caused by GIC events? Oh, I think we might have you there on mute, Abel. Oh, 1 second. I think I know how to fix that. I kicked it on. There we go. All set. One more time on the mute.
Okay. Are we good now?
We are good.
Okay, so, sorry about that.
Just got to give it a Fonzie kick,
Yeah. So, well, this is an interesting and very complex and very, I would say, up-to-date topic, because it's something that's been happening for a long time, but it's only in the last maybe 20 years that it has, gathered a lot of attention from different perspectives, whether the GICs affect the protection system as a whole, different elements in the protection system, whether it affects the transformers, the generators, etc. There are studies that show that, first, not every transformer out there is affected by GIC. And therefore, the first thing you have to do is figure out if your transformer, in particular, given the type of transformer that you have, the manufacturing type, the core type, etc., that the transformer has, it will be affected by the GIC event. The second thing is, I would recommend those who are asking that question to go and read a very comprehensive report by the PSRC, and it's a very recent one. It's only like 2 or 3 years old, which talks and describes the effects of GIC in the system, where the GIC is more likely to affect the system, and also how do we protect the system against the effects of GIC, and also the effects of GIC events. And for those that do not know what we're talking about, I'm sorry, I should have said that in the beginning. GIC means geomagnetically induced currents, which are things that happen in the system. They happen frequently in the system, and even though there's a lot of hype out there, whether these events are caused, very frequently and whatnot. The reality is that they very rarely cause any sort of real damage in the system. It's not to say that they haven't caused that, but it's not as frequent as one think they really are. Now, when it comes to the transformer itself, the transformers protection systems that we discussed, we talked about, Tsugosh discussed overcurrent. He talked about the REF, restrictive earth fault protection, and the differential elements, and they will all be somewhat affected by the GIC event. However, there's two things to keep in mind here. First, every one of those protection elements, especially those protection elements that are designed with microprocessor relays, they operate mostly on the fundamental component of the current that is circulating through the transformer. And that's very relevant, because one of the first things that a GIC event will cause is a high amount of harmonics, but it will not affect very much the fundamental component of the current. And that's one of the first reasons why the protection elements that we have in the systems are not very much affected by the GIC events. The second thing is that GIC events, they tend to produce an increase in the inrush current into the transformer, which affects us in two different ways. One, it will affect the protection of the transformer itself by increasing the transformer magnetizing inrush, but again, the protection systems that protect transformers are typically protected against something like that, because the transformer itself is designed, and the transformer protection elements are designed to take into account the fact that during energization, the transformer has a huge current inrush, and therefore these protection elements are kind of already hardened against this type of event. And the second way in which that DC component affects us is because it saturates the CTs themselves, the CTs that we use to produce the signals that the relays themselves use. And in that case, the effect of the event, of the GIC event, would be no different than that of the effect of a CT saturation, for which we also have measures in place in protection relays. Now, I recommend that whoever is interested go and read that PSRC report, which is very complete, and there's also a few previous studies that were conducted before the PSRC report was produced that go into detail about which transformers may be affected and how do we harden the protection systems to deal with these type of events. Okay.
Thanks, Abel. On to our next question. I'll throw that over to Mohit Sharma. Mohit, what are general settings for negative sequence overcurrent?
Yeah, thanks, Michael, for that question. So negative sequence overcurrent is not used that often for transformer protection, but there are some applications where it is being used. So basically, negative sequence overcurrent is more sensitive to phase-to-phase faults compared with the regular phase overcurrent elements. So the way you set a negative sequence overcurrent is the same way you would set a phase overcurrent element, by doing some coordination analysis. But you have to make sure that your negative sequence, the negative sequence pickup, is such that it is more sensitive to the phase element. So there are ways to achieve that, and you can actually consult relay manufacturers. They can provide you the detailed step-down procedure of how you can achieve that kind of goal. But usually the thing is, what I've read and seen is, you basically find the downstream phase overcurrent protection element of the greatest coordination concern, right? So you need to find in your system the downstream phase overcurrent protection element of the greatest coordination concern, and then you think negative sequence as an equivalent phase time backup of that particular downstream location. And all you have to do is just provide some coordination margin of 1220 cycles, and then usually the negative sequence pickup would be √3 times the equivalent pickup that you will be defining based on the downstream relay settings, right? So, and then at the end of the day, your goal is to make sure the downstream curve and the upstream curve, so the negative sequence curve should lie in between the downstream phase overcurrent curve and the upstream phase overcurrent curve. So that's the end goal, so that you can protect your system and have negative sequence being more sensitive than upstream element. I hope I answered that well.
I think so. So back over to Abel for our third question. Abel, if the high side CT is saturated due to an SC at the transformer high side terminals, will 87T remain silent even though the fault is inside the differential zone? In other words, how does 87T differentiate an inrush condition against a high side CT saturation condition?
Okay. Well, the question is, if there is a short circuit at the high side terminals and it is inside the zone of protection, should the differential, if that fault also produces a saturation of the CTs on that side, will the 87 remain will the 87 remain silent? Will it operate or will it not operate? Well, if the fault is inside of the zone of protection, the 87 has to operate. Because otherwise, how does the 87 differentiate whether the fault, whenever the fault happens between the CTs that define the zone of protection, the 87 has to operate, because it has no way to know whether the fault was inside the transformer or if it was just outside the transformers, but on the wrong side, let's say, of the CTs. Now, if you are asking if the fault is outside of the zone of protection but very close to the terminals, and the fact that the fault is very close saturates the CTs, and whether the 87 will operate or not, well, in that case, if the directionality of the current goes on the other direction, then in that case, yes, the 87 element has ways of dealing with that kind of, let's say, condition in which you have a fault just outside of the zone of protection, with a very high amount of current that saturates the transformer. Now, it's not the same when you have an inrush condition in which you have a lot of current on one side, which has a very well-defined signature, and which happens under conditions where you have very little load on the other side of the transformer. The current that you get, the signature of the current that you get out of that is very well defined, and that inrush condition is defined by the high component of second and fourth harmonics that we have in the signal, right? In the current signal. However, when you have high amount of current on one end and you have saturation of the CT at the same time, then the transformer previously was not in the same condition as the high inrush condition that we were previously discussing, because there was probably some load circulating through the transformer. There is a huge amount of current which will be seen by the CTs on both ends. Those that high amount of current will not be seen only by CTs on one end, like you have in the case of the enrich. In this case, you will have current seen by the CTs on both ends, and that's why we have the things like a dual slope characteristic in the differential protection, or that's why you have things like high security mode in other relays to deal with that condition. So I'm going to say that that's the way the transformer will differentiate between, let's say, a fault. And again, if the fault happens inside of the zone of protection, even though it happens at the transformer terminals, that the differential protection has to operate. But if it happens on the other side, then that's where all the description that I've done right now applies. Okay.
Thanks, Abel. Moving to our next question over to Mohit. Will this REF see internal face-to-face fault?
Okay, so REF if you produce the full form of REF, it's restricted earth fault, right? So usually, as Subhosh was explaining in his slides, REF involves a directional element. It takes a polarization quantity and an operating quantity. Polarization quantity being a quantity which is constant throughout the fault scenario, and it's not affected in any kind of fault. So that's how the polarizing quantity is chosen. So usually in this case, for restricted earth fault, usually it's the ground current that goes through the neutral winding in a grounded transformer system. So for a face-to-face fault, internal face-to-face fault, there would be no ground current flowing through the neutral for a grounded system. So there is no polarizing quantity, right? So meaning that REF element will not operate for that. So for face-to-face, we have phase differential.
Go ahead. I'll throw another question over to Abel. What should one do if transformer damage curves aren't available by the manufacturer?
Well, that's another interesting question. If the transformer damage curve is not available from the manufacturer, what I would do is I would try, it depends how old the transformer is, but there is information on the IEEE standards. There are guides that deal with how to construct the fault curves for the damage curves, for different types of transformers, whether they are oil filled or dry type transformers, and they classify the transformers in different classes, class 1, 2, 3, 4, depends on the type of transformer. So that would be the way to go if you need to have the damage curve and you don't have that information from the manufacturer, perhaps because you have a very old transformer. Because for newer transformers, you are supposed to require that information from the manufacturer. But you can get some guidance on how to produce the fault guide from the IEEE guides, and it will depend, of course, on the type of transformer that you have and the classification of that transformer according to those guides. Okay.
Thanks, Abel. Yeah. I'm going to throw the next question over to Sugosh. Why should we use two slopes in a transformer differential?
Can you hear me, Michael?
Yep.
Okay, thank you. So, like I mentioned earlier during my presentation, so the second slope, right? We saw there's a first slope. There's a reason why we're using slope, to differentiate between the external and internal faults in a transformer as well. It's given a bit more like a percentage setting, because to compensate for different steady state errors. Like, for example, when we talk about slope 1, you would choose like the CT errors will be taken into consideration, the relay measurement errors, and there are different errors that are used to design your slope setting. Now, when it comes to slope 2, which is the second slope, it's used more for your transient error compensation. So let's say you have CT saturation because of a high magnitude through fault. Then that is why the slope 2 is set higher than slope 1. Let me just pull the percentage differential. Okay, so that's where you see that slope is set higher, where you have the ability. Well, the differential would not trip, even though the currents that are being read on those CTs from those CTs to the relay are higher. It would be still be in the restrained region and let the overcurrent relay trip for the type fault at that point, because it's a through fault. So that's why it's important to use two slopes. Hope I answered that question.
Thanks. I'm going to throw our next question over to Mohit. What is the purpose of using the fourth harmonic? Isn't the second harmonic enough?
Yeah, so that's a good question. So as Sugosh mentioned, second harmonic is used to protect against magnetizing inrush conditions. We don't want transformer differential to operate for those conditions. So basically, second harmonic will restrain differential from getting operated. But fourth harmonic is kind of like a multiple of second harmonic. So it provides some added leverage, provides some added margin for not operation, right, during the magnetizing inrush. So that can happen like if you have a very modern core and since the transformer sees the second harmonic really low, so maybe fourth harmonic can provide a better margin. But you would never involve just a fourth harmonic. Of course, it would be either an average of second and fourth, or some kind of like a combination summation of second and fourth. So depends on the transformer. Yeah, so modern transformers may need both second and fourth, or even other multiples. So, yeah.
All right. Thanks, Mohit. I'll throw another question over to Abel. Which transformer would require reverse power protection?
Hi. Yeah, another interesting one, because the reverse power is not a protection that you would say it's a protection only for transformers. It's you apply reverse power whenever you believe that the power flow in any line in the system should only go in one direction, or when you don't want the amount of reverse power that transits to a particular place in the system to be higher than a particular number. So with that in mind, it's not for the protection of the transformer. It's more for the protection of the system that we use reverse power. Now, let's not confuse reverse power with directional protection, which is used more for coordination than for the actual implementation on a particular philosophy of protection. And I say that knowing that a lot of times reverse power elements are used as polarizing elements for overcurrent protection, thus turning that overcurrent protection into a directional protection, which is, I guess, one way of achieving directionality. Okay?
All right. Excellent. I'll send another question over to Sugosh. Why not use 4.2 settings on the restraint?
Okay, I believe it was from the example that I explained. Let me try to pull that up. Okay. So okay, over here. So if you choose 4.2, which would be lesser than the tap setting is used as your reference, right, for winding 1 and 2 for the relay to do its calculation, right? That's what it's tapping it off. So if you choose 4.2, it's lesser than your actual full load amps, obviously on the secondary, it's lesser than that. So you would not want to do that for sure, because now you're compromising your protection ability by choosing a tap which is lower than your actual FLA, right? So that's why it's always better to choose with electromechanical relays. It's always better to choose very closer to what value we have, which is 4.6 in this case, which is a little higher. We do see there is a mismatch percentage, but that is the best we can do.
All right, thanks. I think we've got time for one last question today. So I'll send that over to Mohit. Why is the minimum operating pickup equal to 0.3? Can this be a different value?
Yeah, absolutely. It can be a different value. Well, it all depends on a variety of factors, which Sughosh touched briefly. So the reason it all stems from the fact that what's the purpose behind having a percentage restraint characteristic? So it could be to compensate for the CT errors on either side. It could be to compensate for the CT accuracy levels. Any kind of, if you have a tap changer, on-load tap changer, it would be to avoid any errors due to that. Or like for electromechanical relays, you have this tap, which Sughosh just mentioned. We have limited taps on the nameplate to put our screws in. So all these account in defining the 0.3 PU level of the minimum pickup. So everything related with CT accuracy, CT mismatch, all the steady state errors define that level. So it could be anything depending on the transformer that is in place or the system it has been used at.
Thanks, Mohit. And while I have you, I'd like to tack on one more question to you. Does your test sets accommodate outputs to where current and voltage sensors are used in place of traditional iron core CRs and VTs? For example, a traditional CT output amp versus current sensor millivolts.
Yeah, so I believe the question is related with the sensor technology that a lot of relays these days are having. For currents, they usually have like either a Rogowski coil sensor or a low power current transformer sensor for detecting the millivolt and seeing basically the CTs. Rogowski CTs are used to avoid CT saturation problems that can happen in traditional CTs, but the output of those Rogowski sensors are in millivolt. So I believe the question is towards that direction. So the answer to that one is yes, we do have products now which you can use as part of the SMRT series of equipment, which is our traditional relaying equipment. And we do provide testing solutions and cables to be used for a variety of relays from ABB, Siemens, Schneider Electric that uses these sensors to detect CT signals. And for the VT, we do same goes with the VT. So low voltage VT signals, these relays have Ethernet ports to see the low voltage signals as sensors, and we do provide solutions both for CTs and VT low level outputs. So you please feel free to get in touch with either engineering or technical support group. I think Michael's going to provide, yeah, there you go. On the slide, you see the information. So you can get in touch with Sughosh, and we would be more than happy to help you answer more questions of that. Or if you need more information, we can provide you some data sheets that we have on that product.
Yeah, absolutely. You can also find those links over in the related links window on your screen if you'd like to pop over to those product pages and download some data sheets. But that does look like we've run out of time here today. We're slightly over our hour-and-a-half mark. But I do want to thank everyone for attending today. We apologize if we didn't get to your question live here. We're going to be working to follow up with you offline as soon as possible to get those questions the answers and time they deserve. But as a reminder before everyone leaves, a copy of your presentation, a certificate of attendance, and a link to the recording of the webinar will be sent in about 2 business days. I'd like to thank you all again for attending. After we conclude here, the survey should pop up on your screen. We'd greatly appreciate it if you could take a couple of minutes to answer that and let us know how we did, how we can do better, and what you'd like to see in the future. Additionally, there's a field for you to request a quote or a demo on any of the mega products you saw here today. But once again, I'd like to thank you all for attending, and I hope you all have a great weekend. All right. Bye, guys.
Thank you, guys. Thanks for attending.
Thank you all.